Hello everyone, welcome to this session. In this session, we are going to discuss some more general methods to find inverse Laplace transform. In our previous session, we have discussed inverse Laplace transform of derivative of f of s and we solved some examples. In this session, we focus on inverse Laplace transform of integral of f of s and inverse Laplace transform of s into f of s, multiplication by s, and finding inverse Laplace transform of the expression which is in the form of f of s by s. And we solve some examples on these three properties. First one is, if L inverse of f of s equal to f of t, then L inverse of integral s to infinity f of s ds equal to f of t by t. Using this property, this is inverse Laplace transform of integration of f of s. So using this property, let us solve this example. Here, first consider given function as f of s. So here, let f of s equal to s by s square plus a square whole square. Now after considering given expression as f of s, now according to this property, here L inverse of integral s to infinity f of s ds equal to f of t by t implies t into L inverse of integral s to infinity f of s ds equal to f of t, right? That means t into inverse Laplace transform of integral s to infinity f of s ds equal to f of t means L inverse of f of s. Now let us replace this general term f of s by this particular expression. Then we get t into L inverse of integral s to infinity s by s square plus a square whole square ds equal to L inverse of s by s square plus a square whole square. Now before integrating this expression, here this is derivative of, we can write one adjustment, here L inverse of integral s to infinity, here 1 by minus 2 into minus 2s by s square plus a square whole square ds. Here I have multiplied and divided by minus 2, which is equal to L inverse of s by s square plus a square whole square. Now here this is nothing but t into L inverse of minus 1 by 2 into integral s to infinity minus 1 by 2 into integral s to infinity. Here minus 2s by s square plus a square is nothing but d by ds of 1 by s square plus a square ds equal to L inverse of s by s square plus a square whole square. Since derivative of, since d by ds of 1 by s square plus a square equal to minus 2s by s square plus a square whole square. How do you get this? Here we can get this here in this form. Here d by ds of, this can be written as s square 1 by x. First apply 1 by x formula. So minus 1 by, so what do you get if you differentiate this? This is in the form of 1 by x. So what is d by dx of 1 by x? D by dx of 1 by x equal to minus 1 by x square. But here in the place of x, here s square plus a square is there. Here power is not 1. That's why after applying this formula, we have to differentiate this denominator again. That means minus 1 by s square plus a square whole square into derivative of s square plus a square. So derivative of s square plus a square is 2s. Derivative of s square is 2s. Derivative of a square is 0. That's why here we get minus 2s by s square plus a square whole square. So here first we have adjusted this number here in this integrand. First we have inserted minus 2. That means by dividing and multiplying by minus 2, we have inserted minus 2 in the numerator. Then we have written this expression as derivative of d by ds of 1 by s square plus a square. Now to integrate this, whenever you want to integrate this, here integration and derivative, these two get cancelled. We get which is equal to t into L inverse of minus 1 by 2 into 1 by s square plus a square but we have to apply limits. Here limits are from s to infinity, which is equal to L inverse of s by s square plus a square whole square. RHS as it is, no change. Now let us apply limits. So t into L inverse of minus 1 by 2 into 1 by infinity plus a square. So 1 by infinity minus 1 by s square plus a square equal to L inverse of s by s square plus a square whole square. Now 1 by infinity is 0. So we get t into L inverse of minus 1 by 2 into 0 minus 1 by s square plus a square equal to L inverse of s by s square plus a square whole square. Here RHS is given question. That's why we are continuously writing RHS as it is without changing that. Now here t into L inverse of, if you multiply these two, you get 1 by 2 into s square plus a square equal to L inverse of s by s square plus a square whole square. So t into 1 by 2 you can take outside, L inverse of 1 by s square plus a square equal to L inverse of s by s square plus a square whole square. Now L inverse of 1 by s square plus a square equal to 1 by a sin 80. So using this formula, if you apply this formula on left hand side, we get t into 1 by 2 into 1 by a sin 80 equal to L inverse of s by s square plus a square whole square. Therefore, inverse Laplace transform of s by s square plus a square whole square equal to t into sin 80 upon 2a. This is required solution. Now let us see next property. Next property is also called multiplication by s. Here if L inverse of f of s equal to f of t, then inverse Laplace of s into f of s equal to f dash of t if f of 0 equal to 0. Here f dash of t means you can write in this manner also, d by dt of f of t. That is d by dt of inverse Laplace transform of f of s. Now let us see working method. First write given expression in the form of s into f of s. Then apply inverse Laplace transform on s into f of s and use this property. That means you have to differentiate L inverse of f of s with respect to t. Now find L inverse of f of s here. First we have to find this inverse Laplace of f of s, then we have to differentiate this with respect to t to get the final answer. Now let us see this question. Find inverse Laplace transform of s by s square plus a square. Now s by s square plus a square can be written as s into 1 by s square plus a square. So when we are finding inverse Laplace transform, L inverse of s by s square plus a square can be written as L inverse of s into 1 by s square plus a square. So this is in the form of s into f of s. So we know that property. What is that? L inverse of s into f of s equal to L inverse of s into f of s equal to d by dt of L inverse of f of s. D by dt of derivative of inverse Laplace transform of f of s if f of 0 equal to 0. Now let us apply this property. If you apply this here, identify f of s first. So f of s equal to, this one is f of s equal to 1 by s square plus a square. Now let us find inverse Laplace transform of f of s, which is equal to f of t, which is equal to L inverse of 1 by s square plus a square. So L inverse of 1 by s square plus a square equal to 1 upon a sin at, because L inverse of 1 by s square plus a square, this is formula of inverse Laplace transform, which is equal to 1 upon a sin at. So we have applied this formula here. This is already in the form of this formula only, so we have written 1 by a sin at. Now after finding this, you have to differentiate 1 by a sin at, because here L inverse of s into 1 by s square plus a square equal to d by dt of L inverse of f of s, that is 1 by s square plus a square, which is equal to d by dt of 1 by a sin at. Here this condition, if f of 0 equal to 0, here f of t equal to 1 by a sin at. Now f of 0 equal to 1 by a sin 0. As value of sin 0 equal to 0, value of sin 0 is 0, you get 0. So this condition is satisfied, f of 0 equal to 0. Now let us differentiate 1 by a sin at. Now d by dx of sin ax equal to a cos ax. Now if you apply that here, 1 by a is constant, so 1 by a into here cos at, a cos at, a cos at. Now a and a will get cancelled, we get cos at. Okay, but when you observe, here we have derived this cos at by applying this property, but L inverse of s by s square plus a square, you know its formula. L inverse of s by s square plus a square equal to cos at only. So we have obtained cos at by using multiplication by s property. Okay, so you can verify. This is standard formula. This is inverse Laplace of elementary function. Okay, so inverse Laplace of s by s square plus a square equal to cos at. We know that, but we have obtained this formula or this value cos at by applying multiplication by s property here. Now let us see next property. Here, division by s, inverse Laplace transform of f of s by s. Here, if L inverse of f of s equal to f of t, then L inverse of f of s by s equal to integral 0 to t f of t dt. Now, here from given question or given expression, first write it in the form of f of s by s, because we have to identify f of s from given expression. So, to identify f of s, first write given expression in the form of f of s by s. Then find inverse Laplace transform of f of s to get f of t. Then integrate f of t with respect to t under the limits 0 to t to get inverse Laplace of f of s by s. So here I have listed 3 questions here, 3 problems. So let us solve one by one. First one, find inverse Laplace transform of, find L inverse of 1 by s cube into s square plus a square. S cube into s square plus a square. Here, if you find s cube, you have to integrate thrice, 3 times. Okay, because L inverse of f of s by s we know, which is equal to integral 0 to t f of t dt, implies L inverse of f of s by s cube equal to integral 0 to t, integral 0 to t, integral 0 to t, here f of t dt, again dt, tripling. You have to integrate thrice after obtaining this f of t. So let us integrate one by one. So let us consider s first, then s square, then s cube. Okay, so let us consider here f of s. Let us consider L inverse of 1 by s into s square plus a square first. First let us find this one. Now we can write this as L inverse of 1 by s square plus a square upon s. So this is in the form of f of s by s. F of s by s. So f of s equal to 1 by s square plus a square. Now we have to find f of t. F of t is nothing but L inverse of f of s. So which is equal to L inverse of 1 by s square plus a square. So according to elementary functions formula, here we get 1 by a sin 80. 1 by a sin 80. Now L inverse of f of s by s, L inverse of 1 by s square plus a square or s into s square plus a square equal to integral 0 to t 1 by a sin 80 dt. Now integral sin x dx, integral sin x dx equal to minus cos x. Apply this formula here. So here we get 1 by a but here at is there. If you consider ax here in the place of x, here you get minus cos ax upon a. So here we get minus cos at upon a under the limits 0 to t. That means 1 by a. Now let us put t equal to t by a. Whenever we apply lower limit, sign changes. So here plus cos 0 by a, which is equal to 1 by a into minus cos at plus 1 upon a. Here I have taken LHS and I replaced cos 0 by its value, that is 1. So this is nothing but 1 minus cos at upon a square. So if we integrate once, we got 1 minus cos at by a square. Now to get L inverse of 1 by s square into s square plus a square, we have to integrate the expression whatever we have obtained just now with respect to t, that is 1 minus cos at by a square dt. We have to integrate this, that is 1 by a square integral 0 to t 1 minus cos at dt, because in our previous side here we have obtained 1 minus cos at by a square. We have to integrate it again with respect to t. So not derivative, integral 1 dx equal to x, then integral cos ax dx equal to sin ax upon a. So when you apply those formula here, but here variable, independent variable is t, that's why here integration of 1 is t minus integration of cos at is sin at upon a under the limits 0 to t. That is 1 by a square t minus sin at upon a. When you apply lower limit, you get 0 in the place of t, again plus sin 0 upon a. As sin 0 is 0, you get 1 by a square t minus sin at upon a. So this is inverse Laplace of 1 by s square into s square plus a square. But we need inverse Laplace transform of 1 by s cube of s cube into s square plus a square. To get this inverse Laplace transform, again we have to integrate 1 by a square into t minus sin at by a with respect to t under the limits 0 to t. So here 1 by a square integral 0 to t minus sin at by a dt. Here d by dx of integral x dx equal to x square by 2 and integral sin ax dx equal to minus cos ax upon a. Use these integration formulae to integrate these terms. So we get 1 by a square, here t square by 2 minus 1 by a into minus cos at by a under the limits 0 to t. Here a is constant, so first we have written 1 by a as it is, then we have integrated sin at using this formula minus cos at by a. Now we have to apply limits. First apply upper limit. When you apply upper limit, no change, we get 1 by a square into t square by 2, here minus into minus plus cos at upon a square minus 0. When you put t equal to 0, you get minus 0 by 2 minus cos 0 by a square. That is 1 by a square into t square by 2 plus cos at upon a square. Third term is 0 and fourth term is minus 1 by a square, because value of cos 0 equal to 1. So this is required inverse Laplace transform. Inverse Laplace transform of 1 by s cube into s square plus a square. Now let us see next question. 1 by s into find L inverse of 1 by s into s plus 1 whole cube. So you can write it as L inverse of 1 by s plus 1 whole cube upon s. So if you compare this with f of s by s, you can find f of s. So f of s equal to 1 by s plus 1 whole cube. Now to get f of t, find inverse Laplace transform of this f of s. That is inverse Laplace of 1 by s plus 1 whole cube. Now to get inverse Laplace transform of this, we apply this formula L inverse of 1 by s plus a whole raised to n. Let us write some n plus 1 equal to e power minus at into t power n by n factorial. Apply this formula to get inverse Laplace of this expression. Now, so this is equal to, according to this, here e power minus t. Compare this, in the place of a you can find 1. So here we get e power minus t into t power n. T power, here n is 1 less than n plus 1. So here you have to consider the number 1 less than this power, that is here it is 3. So if you subtract 1 here from 3, you get t square upon 2 factorial. So 2 factorial is e power minus t into t square upon 2 into 1, which is equal to e power minus t into t square upon 2. Okay, this is f of t. Now we want to find L inverse of 1 by s into s plus 1 whole cube. That means according to that property, we have to integrate this f of t, e power minus t into t square by 2 with respect to t under the limits 0 to t, because L inverse of f of s by s equal to integral 0 to t f of t dt. That's why whatever we have obtained here in the place of f of t, we have to integrate it with respect to t. So if we integrate that with respect to t, we get L inverse of 1 by s into s plus 1 whole cube equal to integral 0 to t e power minus t into t square by 2 dt, which is equal to 1 by 2 into integral 0 to t e power minus t into t square dt. Here you can apply UV rule or integral UV rule, or you can apply general integral UV rule. Here integration UV equal to UV dash minus U1 V double dash plus U2 V triple dash minus so on. Here U1, U2 so on are derivatives, and here V dash, V double dash, V triple dash are integrals. So whenever you are applying this general UV rule, consider the term which has finite number of derivatives as u. Here consider t square as u, because if you consider t square as u, then first derivative u1 equal to 2t and second derivative here u equal to t square. Derivative of t square is 2t. Again derivative of 2t is 2. Third derivative is 0. So t square has finite number of derivatives, first derivative and second derivative. So consider t square as u and e power minus t as v. Okay, so here v equal to e power minus t. v dash means integration of e power minus t dt. That is e power minus e power minus t. That is e power minus t by minus 1, which is equal to minus e power minus t. Now v double dash means integration of minus e power minus t dt again. So which gives minus of minus e power minus t, which is e power minus t. Okay, now let us apply this general UV rule to integrate this. So 1 by 2 into, according to this formula, according to this general UV rule, we get 1 by 2 into, here this is u. In the place of u, we should write t square into, in the place of v dash, we should write integration of e power minus t. That is minus e power minus t minus derivative of t square, that is 2t, integration of this minus e power minus t, that is e power minus t, here plus derivative of 2t, that is 2, into again integration of e power minus t, that is minus e power minus t, under the limits 0 to t, which is equal to 1 by 2 into minus t square e power minus t minus 2t e power minus t minus 2 e power minus t under the limits 0 to t. So when you put t equal to t, you get same terms. So minus t square e power minus t minus 2t e power minus t minus 2 e power minus t. Whenever we are applying lower limit, signs of these terms will change. So here plus, when you put t equal to 0, first term becomes 0, plus even second term becomes 0, but here third term 2 into e power 0. As e power 0 is 1, we get 1 by 2 into, here 2 into 1. So 2 minus t square e power minus t minus 2t e power minus t minus 2 e power minus t. So this is inverse Laplace transform of 1 by s into s plus 1 whole cube. Now let us solve third question. Find inverse Laplace transform of, let us see the third question once. Third question is 1 by s into s plus 4. Find inverse Laplace transform of 1 by s into s plus 4. That is L inverse of 1 by s plus 4 upon s. As usual, we have written this in the form of f of s by s to identify f of s. So f of s equal to 1 by s plus 4. Then we have to find f of t. To get f of t, we have to find inverse Laplace of this 1 by s plus 4. So inverse Laplace of 1 by s plus 4 is e power minus 4t. Since inverse Laplace transform of 1 by s plus a equal to e power minus at. So here, to get inverse Laplace of 1 by s into s plus 4, we have to integrate this e power minus 4t with respect to t under the limits 0 to t. We know integration of e power ax dx equal to e power ax upon a. So we get e power minus 4t upon minus 4 under the limits 0 to t. So which is equal to minus e power minus 4t upon 4. Whenever we apply lower limit, this becomes plus e power 0 by 4, which is equal to minus e power minus 4t by 4 plus 1 by 4. If we take LCM, we get 1 minus e power minus 4t upon 4. So L inverse of 1 by s into s plus 4 equal to 1 minus e power minus 4t upon 4. So in this session, we have discussed three properties: inverse Laplace of integral of f of s and inverse Laplace transform of s into f of multiplication by s. So inverse Laplace transform of the expression in the form of f of s by s. Three properties, and we have solved some examples based on these three properties. So under general methods, all these properties, whatever we have discussed in general methods part 1, part 2 and part 3, all these properties, they come under general methods. So in the next session, we focus on partial fraction method. That means finding inverse Laplace transform using partial fraction method. So thank you. Let us meet in next session.